So we've simplified the heat equation and seen that when we apply those four kind of classic simplifying assumptions, that we can conceptually model a thermal physical system as basically a thermal circuit, right? And afterwards, we started asking ourselves, well, what happens if we start bringing stuff back in, right? So we make the assumptions, we generate the idea of a thermal circuit, but if we start removing assumptions, can we still work with the thermal circuit model? What changes do we have to make? What stays the same, all right? And what the point of this lecture is going to be is to try to relax the assumption that the heat transfer inside of a system that we're trying to model using this notion of a thermal circuit, we're trying to relax the assumption that the heat transfer has to happen in exactly one direction, right? The one-dimensional heat transfer maybe can be two or even three-dimensional heat transfer. So what are the sorts of scenarios that we can consider in the process of trying to relax this assumption? Well, consider the following. So suppose that I had some kind of, cylindrical wire, which is either being heated up or is at a high temperature, which is surrounded by a rectangular casing, okay? And so you can imagine that this is a three-dimensional object with some, length. And then we can also say that maybe it has a side length, A. For the purposes of this particular problem, we're just going to assume that this cross-section is a square, but it doesn't actually have to be. This is just for convenience. Let's suppose that this circle on the inside has some radius, r. Okay? And so this geometrically fully defines the object that we're working with. Now, we can hypothesize that maybe this interface here between the cylinder and the square is at a temperature T1, okay? And we can assume that the interface between this, rectangular kind of casing and whatever else it's in contact with, say either like atmosphere or air, or even maybe encased inside of some other thing, whatever that thing is, the interface between it and this square or rectangular object is T2, all right? That's the temperature at the interface. And so we can ask ourselves if this has some thermal conductivity K, right? I mean, it makes sense, right? We're assuming that this is a solid material, so it has some thermal conductivity. So if this material here has a thermal conductivity K, what is the heat transfer rate that's happening through it? Okay, what is the heat transfer rate going in, which by extension has to be the same going out because there's no energy being generated, and because we're also going to assume that the system is in steady state. So the assumptions that we're making for this problem, we're going to assume that there's no thermal energy generation anywhere inside of my system, all right? Although technically speaking, the only place where it matters is in the thing that we're trying to analyze, which is this square, rectangular thing. We are also going to assume that material properties are constant. And so from that perspective, right, this K is a single number. It doesn't vary as a function of distance away from, it doesn't vary as a function of where we try to analyze heat transfer in the system or anything like that. We also are going to assume, like I just mentioned, that the system is in steady state. All right, so these temperatures are the temperatures forever. This K is the thermal conductivity forever. These geometric properties are the same forever, okay? What we cannot assume is that heat transfer is one-dimensional. We can't assume that. And the reason that we can't assume that is because now, because we have the heat transfer going from a circle to a square, we lose the symmetry that tells us that the heat transfer is happening radially outwards. Now, it makes sense for us to say intuitively, oh, well, the heat transfer is just happening outside, right? It's going in this direction or this direction. But notice that that changes, hypothetically speaking, right? If you are here, it's easy to draw a heat flux vector that's pointing into the square from the circle. And it's easy over here to say, this is a heat flux vector that is pointing out from the square into whatever else is here. But because these directions don't align, right, because one of these is radial and the other is planar, then heat transfer that's happening inside of the system is not one-dimensional, right? It's two or even potentially three-dimensional. So how do we model it? Well, here's an interesting little idea that jives well with what we've been doing so far in terms of trying to make our lives easier by coming up with simplified mathematical expressions for things. What we want to try to do is see if we can't represent the relationship between the heat transfer rate that is happening through, this square or rectangular thing with a hole in it, if we can't relate that to the difference in temperatures between T1 and T2, okay? Because that's what we always do with thermal circuits. So we want to try to see if we can't find some function that relates Q to delta T. Now, you may already know where this goes, right? We have already described how you linearize expressions in order to be able to get something where you can say, oh yeah, this is just a linear function of delta T. But there's actually something much more interesting that we can do here, which is good practice, not just for the study of heat transfer, but also for other physical fields where we have to do this kind of like fun little trick, which is dimensional analysis. Okay, so what does that mean? Well, let's consider all of the different properties that make this system what it is, right? What are the things that I can change that would make this system different? And what are the things such that if I precisely define what they are, I know that I have the exact same physical system? So for example, if I pin down the same value of A and R and K and T1 and T2 and L in two different experiments, it should be the case that I get the same physical result, right? Because I've made all of the physical variables that affect heat transfer, as far as we know, in this system the same. And so if the inputs are the same, so to speak, the outputs have to be the same too. That's the idea. And so let's list out those parameters, okay? So what are the things that affect the behavior of this system? Well, T1, T2, K, R, A, and L, okay? And technically speaking, T1 and T2, at least based off of our idea of how heat transfer works, shouldn't necessarily affect the behavior of this system directly. It might, but if we assume that the material properties are actually constant, then based off of the idea that heat transfer only occurs as a result of temperature differences, this should actually be just a function of T1 minus T2. So we don't have to worry about the individual temperatures, we only have to worry about their difference. If we make this assumption, what do we find? Well, we have a temperature difference, we have a thermal conductivity, and then we have a bunch of parameters that describe the geometry, right? The shape of this object. And what we're trying to do is we are trying to write what the heat transfer rate is through this little thing as a function of these parameters which I've written down over here, right? R and A and L, and so on, right? So, is there any particular way that I can narrow down what this function is without necessarily having to do a linearization? Well, there is. Suppose that I were to write the following statement. Suppose I were to just say this. Now, whether or not this is correct or not is not the point. ask yourself, is this a statement that even makes sense? Is me saying that Q is equal to 5 a meaningful sentence? And the answer is no. And the reason that the answer is no is because this is a number and this is a heat transfer rate. If I had said that this was 5 watts, now we would get something that makes sense. But me saying that Q is equal to 5 is like me saying something like, oh, the sky is looking pretty dog today, right? It doesn't make sense. It's not a statement that's coherent. And this little principle, right, that we have to make things on either side of the equations that we construct coherent is actually surprisingly, maybe even shockingly restrictive statement on the kinds of functions that we can get, right? Because to make my claim a bit more concrete, this is also a nonsense statement, right? Because this has units of watts, and this has units of watts per meter degree Celsius, or watts per meter Kelvin. And so I can't say that this is equal to this because they're not the same physical quantity. So this invites a question. What are the things that I can construct out of these variables that will give me something that has units of watts, right? What are the things that I can say that this is a function of? Okay, well, let's take a look at the units for these things, right? So Q, we had already mentioned, had units of watts. T1 minus T2 has units of temperature, technically temperature difference. The distinction is not super relevant here. And so from the perspective of just being consistent, we're just going to pick to represent this temperature difference using Celsius. Okay? So that's the units of a temperature difference. The units of K is units of watts per meter degree Celsius. Okay? Just like we had derived before. And then the units of R and A and L are just meters. Okay? So you can already kind of see algebraically how we can try to construct something that has units of watts in this expression. So how do we do it? Well, we know that if this has to have units of watts, we know that the K has to show up over here, right? So now we have something that has units of watts per meter degree Celsius. Now we want to get rid of the meter and the degree Celsius. So what do? Well, we just multiply by the thing that has degree Celsius units. So we multiply by T1 minus T2. All right. So what's left? Now the resulting thing has units of watts per meter. And so what we want to do is to multiply by something that has units of meters. But we have a bunch of different things that have units of meters. We don't actually know if this should be A, or if this should be R, or if this should be L. Even worse, we don't even necessarily know whether or not it's a single one of them. I mean, it stands to reason that it should be a function of both R and A and L, right? So this thing is some unknown function of R and A and L that we don't necessarily know. So how do we try to find F? That's a good question. And the way that we usually find what this function is via either doing numerical simulations of systems like these or by doing experiments. But the interesting fact about this is that we've converted this problem from being something where we didn't know at all what this heat transfer function was. We've converted this into a problem where now we know the dependence on the thermal conductivity and the temperature difference. We just have to find what this geometric function is, which is only a function of the parameters that describe the shape of the system, right? And we also know that this thing, this function, whatever it is, it has to have units of meters, right? Because it's the only way that this is dimensionally compatible, that the stuff on the left has the same dimensions as the stuff on the right. And so this thing, this function that we don't know about, is usually referred to with the symbol S. And then we say that S is the shape factor of the system. Right? So we say that S is this thing that is only a function of whatever the shape of our particular like goofy looking system is. We find it by looking up some table in a book or by doing some experiments to figure out what this shape factor is. And then we plug it into this expression in order to get the heat transfer rate through the system. All right? Now, sometimes, especially when you have heat transfer that is happening throughout systems that have some kind of symmetry in one dimension, you'll see that this S gets factored out. So like some people might divide the S by like a factor of L and then get something that's not dimensional, but that is a little too confusing for our taste. The important part is that this is the general expression, okay? And that this S contains all of the information about the shape of the system. And so you can imagine, right, that if I had a system that was similarly configured, so for example, let's say that I had a non-concentric set of, wires. So I have a wire, just like I did before. It has some radius R, let's say R1, and then this is located non-concentrically inside of some other, cylindrical object, which has radius R2, and we can imagine that it has some like length L. And we might wonder, well, what is the heat transfer that's happening through this secondary object here? In that scenario, it's very, very similar to what happened before. As long as we know what these temperatures are, we would look up in a table what the shape factor of this particular geometry is, and then use the value of K and the temperature differences to figure out what Q is, right? According to this equation. So that is how this works. And so you'll find in most heat transfer textbooks, like tables and tables and tables of different images of shapes and systems, along with values of what S is as a function of the things that define that shape, okay? Now, one last thing that I want to mention about shape factors, and it's a relatively simple thing to catch, but it is important, which is that we have this expression, right? So we have the idea that Q is equal to S times K times delta T. And notice that in our previous discussions, I wrote T1 minus T2. It actually doesn't matter if it's T2 or T1. It's that same sign ambiguity about whether or not the heat flux is going inwards or outwards, okay? So without too much problems, we can just write this expression. Now, if I had a situation where, just like before, I had, my non-concentric cylinder, I might ask myself, well, maybe I can model this thing, or even if I have something even more complex, so maybe something like this. This, I can assume, behaves a little bit like a thermal circuit described system, right? Maybe in here, approximately, in this central region, the heat transfer that's occurring between this cylindrical core all the way to the outside does actually, satisfy the assumptions. And maybe the only thing that doesn't satisfy the assumptions is this thing here on the outside, right? Because the heat transfer here is now going to be approximately two-dimensional. So if I tried to create a thermal circuit for this system, the challenge would be that I don't really know how to represent this, right? So if I tried to draw a thermal circuit for this system where I said that this was element 1, this was element 2, and this was element 3, I run into trouble because I don't necessarily know how I can, I don't know whether or not 3 can be placed inside of a thermal circuit because it doesn't satisfy that 1D assumption. Now this example, by the way, has a little trick to it. 1 is also problematic as well. But I want you to think about why 1 is problematic based on the context of previous lectures. This is just a sort of thing. But nevertheless, 2 is perfectly fine, has a perfectly fine representation of the thermal circuit. So can we actually plug 3 in and get something that allows us to analyze this system like a thermal circuit? Like, can we get rid of this problem that is inserted as a result of assuming that heat transfer happens in only one dimension? Sure, because this expression tells me something very, very important, which is that there's a linear relationship between Q and delta T, which means that I can write this down as Q divided by S over K is equal to delta T. And so I can observe that I have an effective thermal resistance. And that effective thermal resistance is just 1 over Sk. So this is pretty neat, because what it tells us now is that it actually doesn't necessarily matter whether or not we have, specific elements that violate the assumption of one-dimensional heat transfer. As long as we can find the shape factors, we can still treat the system using thermal circuit assumptions, assuming the rest of it satisfies it, right? And then effectively represent the thermal resistance of these 2D objects as 1 over Sk. And so this thermal resistance doesn't tell us very much. It tells us that, the higher the thermal conductivity, the lower the thermal resistance. That's expected. But the interesting part is that this shape factor, right, is a function of all kinds of different things. We have no idea what the shape factor function is from first principles unless we actually did some theoretical analyses. But most of the time we pull these from a table or from a numerical experiment. And so we don't actually know how changing individual parameters that govern the shape of the system affects the thermal resistance, only that the thermal resistance is inversely proportional to the shape factor, whatever it is. Okay? And to finish this off, you might say, well, this seems a little bit weird, but you can also think of every other material we've been working with, like every one-dimensional system we've been working with, to also have like a shape factor. Like, we can interpret every conductive resistance through this lens, right? Think about one-dimensional heat transfer through a wall, right? We say that this has a thickness of delta X, and that this has a cross-sectional area of A, and heat transfer is only happening left to right, and this has a thermal conductivity K. Then we had already derived, right, that Q for this particular system was, the Q times delta X divided by K times A is equal to delta T. This is the expression that we had derived, right, for the resistance of a planar conductive element. But notice, right, that we can also just say that this is Q times 1 over Sk is equal to delta T. And in that scenario, the shape factor, right, S, is just the cross-sectional area divided by the thickness. And so the interpretation that we've pulled, the idea of a shape factor, is not just a thing that we've invented specifically for the case where we have two-dimensional heat transfer or three-dimensional heat transfer. It is something that is universal about the way that heat transfer moves through objects, given all the other assumptions that we've made to model it, right? Which is that the resistances associated with all conductive elements will always have this 1 over K dependence, and then we'll also always have this 1 over S dependence, which is just some function of the geometric parameters of the object that eventually has units of meters, which you can see is true here, right? Because meters squared divided by meters is meters. And you can test this out too for the cylindrical ones and whatever. And so this gives us a way to keep using the thermal circuit approach even when we don't necessarily have heat transfer in one dimension.